Welcome to lecture 25 of Power System Protection course. We discussed in the last lecture, that is lecture 24, regarding the generator protection, and also we covered the busbar protection initially. Then we covered few portions of the generator protection, and we saw that generator, in fact, though it's a simple equipment, but being its connection to the other parts of the network, like the output is connected to the grid, the input is connected to the turbine, and also the turbine is being fed by the steam through the governor mechanism, and the steam is being fed from the boiler. So and also there is another component of the generator, that is excitation system. So all these things around the generator makes the generator a complex unit, and it's very important, in fact, to protect the generator, because whenever the fault happens in any of the components of the generator which is being connected to the generator, then the fault, in fact, the disturbance propagates to the generator, and hence it is very important to protect the generator. And we saw in the last class that generator protection for the phase and ground faults, how the differential relay can be used, and that is in case of generator protection, it is known as the longitudinal protection. And in case of because it is named in a different way, longitudinal protection, in case of generator protection, though it's a simple differential relay, percentage differential relay, because because we are using another kind of differential relay which is known as transverse differential relay, which is used to detect the interturn faults in the starter winding. And therefore these two terms are used. One is your longitudinal differential relay, which is a normal percentage differential relay, and another one is your transverse differential relay, which is used to detect the interturn faults in the starter winding. So already we discussed all these things, and let us continue more on generator protection, because there are many other aspects, other components of the generator which also need protection. So in this lecture we'll cover the generator protection, the remaining portion, and then we'll also take static comparators which can be used as relay. Static comparators, in fact, developed after the invention of transistors and the op-amps came into picture, and how by using these small electronic components we can develop the relays, and that is known as the static comparators. And static comparators, how it can be used as used to design different kind of relays. Okay, so let us see first the rotor fault protection in this lecture. So the rotor fault protection, in fact, if we'll consider the electrical faults, so in fact it happens because of the short circuit in the rotor. Rotor means on the field winding. In the field winding, when short circuit happens, that we call the rotor earth fault, right? So this rotor earth fault, in fact, what is the problem, what happens when the rotor earth fault happens? We can see here that when the fault happens, in fact, because when the fault is not there initially, let us say, the current flows in a unidirection from positive to negative, and this is your field winding of the generator, right? Okay, and this is your exciter. So now the current is flowing unidirection, and the flux is being produced, which is linking the armature of the generator, right? And when let us say when the fault happens. So what will happen now when the fault happens? So therefore in this case what happens, there is the mechanism is that for protection, that there is some auxiliary supply we supply through an isolation transformer through a rectifier bridge, and it is connected to the field circuit through the overcurrent relay, right? So in fact this overcurrent relay detects when some current passes through this overcurrent relay, and because another terminal of the rectifier is earthed, and here also when such circuit happens to earth, there is a path of current and which in fact flows through this overcurrent relay, and when the overcurrent relay detects this, it gives the trip command to the circuit breaker of the generator, and also it gives signal to the alarm circuit. So this is how the rotor fault protection works, right? So now we'll see the abnormal operating conditions. In fact, abnormal conditions are not as much severe as the fault conditions, but somehow if the abnormal condition remains or sustains more than the allowed time, then it may happen that this will cause damage to the generators, because we know the generator is very sensitive. The rotor is a huge mass which is rotating with a small air gap. So any abnormality happens and it persists for a long time, then in fact it produces more heat inside the rotor and some deformation may happen in the rotor. So that causes in fact problem to the rotor, in fact to the generator. So let us see what are the abnormal operating conditions. Already we have seen this in the last lecture. There are two major abnormal conditions happens, that the type is one is electrical and mechanical type. And in fact the electrical abnormal conditions happen in starters and in starter circuit and in rotor circuit. In starter circuit means it is in the three-phase starter winding, and in the rotor circuit means it will refer to the field winding. So now how it happens? The abnormal operating condition happens when, because of the unbalanced loading of the generator, and in the rotor it happens because of the loss of excitation. Okay, so because of the loss of excitation, that means when something happened that the excitation becomes open circuited in the generator, right? And the mechanical abnormal operating condition happens when there is loss of prime mover and overspeeding. So loss of prime mover may happen, there may be many causes, because of the somehow the steam supply is stopped to the prime mover, that is loss of prime mover. And overspeeding happens when there is a huge loss of load, right? When the load is certainly off, switched off from this network, then the overspeeding happen in the generators, right? So let us now consider each of these abnormal conditions. Let us first will consider the unbalanced loading. So what happens when the unbalanced loading phenomena happens? In fact, if there is an unbalanced loading of the generator, then obviously the starter currents have a negative sequence component, right? Because we know under balanced condition there will be no negative sequence and positive sequence component. It only happens, it is only produced during the unbalanced condition. So because of this, the starter field, due to these negative sequence currents, rotates at synchronous speed, right? But in direction opposite to the direction of the field structure on the rotor. So what happens is, because of the negative sequence current, it produces another flux which in fact rotates in the opposite direction to the main field, and thus the negative sequence starter armature MMF rotates at a speed of -ns, while the rotor field speed is plus ns. Therefore, there is a relative velocity of 2 ns between these two, and this causes the double frequency currents of large amplitude and to be induced in the rotor conductors and iron. So in the rotor iron, it produces a double frequency current, that we call the eddy current. Previously it produces the single frequency current. Now the frequency becomes double. So when the frequency becomes double, we know that the eddy current loss is directly proportional to F square B max square, while the hysteresis loss is proportional to F B max to the power n, where n varies from 1.6 to 2 depending upon the core material. So therefore, because the frequency increases, right, so therefore the loss in the form of eddy current loss, it increases, and it in fact produces more heat in the core material. Therefore, both the eddy current as well as the hysteresis losses increase due to these double frequency induced currents in the rotor. So that causes in fact more heat, right? So how to avoid this situation? Let us see. So how we can protect, and this is the flow diagram how the additional heat is generated in the rotor circuit, in the rotor core also, right? So when the generator is running in the steady state, it checks whether the unbalanced loading is happening. If it is no, then it is okay. If it is yes, then the negative sequence component in the starter current is present, and the starter armature MMF due to negative sequence current rotates at minus ns per rpm, and that in fact causes the field causes another component of the flux which is rotating in the opposite direction, right? So the relative speed between the rotor and the field due to negative sequence current becomes 2 ns, right? And therefore the double frequency currents of frequency 2 ns p by 120 induced in the rotor core and winding. This is the frequency, double frequency, which is produced in the double frequency current which is produced in the rotor core and winding, and that causes in fact the additional heat generated, as we have seen the formula of eddy current loss and the hysteresis loss. So these both will increase when the frequency increases, right? So then how to protect, or how, if we can, so then our protection scheme should be in such a way that it should identify, or it should detect the negative sequence component of the current, right? So the rate of heat generation is proportional to I2 square R. I2 is your negative sequence component of the current, while the heat energy is proportional to I2 square RT, right? I2 is the negative sequence current, where T is the time for which it is being produced, I2 is the negative sequence current. Since the capacity of the particular machine to safely dissipate energy is limited to a certain value K, right? Let us say the capacity of the machine to dissipate this energy is, let us say, K. We can write the equation if we'll say, so the net heat produced should be equal to K. K is the capacity of that particular machine to safely dissipate the heat energy produced in the machine. So the I2 square RT, that is the energy produced because of this negative sequence component, should be equal to K. Now assuming R to be constant, then your K, capital K, will become K, small k by R. So we get a thermal characteristic of the machine as this, that is I2 square T equal to capital K. And in other words, the time T for which the offending current, this is the offending current, right, because it produces the heat, can be allowed to flow should be less than or equal to K by I2 square. So T will be equal to, from this equation, T will be equal to K by I2 square. Thus the current time characteristic can be written as T should be less than or equal to capital K by I2 square. So this is the time for which your negative sequence current can be flowed in the in the starter. Okay, so we can recall that this characteristic is similar to the extremely inverse time over current relay characteristic, right? So extremely over characteristic we have seen, extremely inverse time over current relay, in which we have seen there is a component of I square, right, in it. So now the same type of characteristic we are getting for this to protect the negative sequence component when under unbalancing situation. Thus an inverse type of overcurrent relay which is fed with the negative sequence component. So that is why if we can somehow feed the negative sequence component to an overcurrent relay having this type of characteristic, that is extremely inverse characteristic, that gives protection against unbalanced loading of the generator, right? So you can see here next how we can implement this, right? How we can implement this. So this is the structure, implementation structure. So this is, we are feeding the starter current, and if we have negative sequence filter that can compute the negative sequence component from the measured quantity, right? So that in fact we can do some numerical, if we can put some microprocessor, it can be possible to calculate the negative sequence component. So after calculating the negative sequence component, this I2 in fact is fed to the overcurrent relay with the inverse characteristic, that is T operating is equal to K by I2 square, and K is set for every machine based on the capability to dissipate the heat energy in the machine. So then if it is less than or equal to this, then it is fine. If it is greater, then the circuit breaker trips, right? So this is the we can say this is the algorithm or implementation process, how we can implement the protection scheme for unbalanced condition in a generator, right? So now I'll talk about the loss of excitation in a generator. When loss of excitation happens, what happens in fact, and how we can protect the generating system. So there are several possible causes due to which the field excitation may be lost, namely loss of field to the main exciter, and second one may be accidental tripping of the field breaker. Third one may be short circuit in the field winding. Fourth one may be poor brush contact in the exciter, and fifth one may be field circuit breaker latch failure. Sixth is loss of AC supply to the excitation system. So these are the 6 causes. These may be the causes of loss of excitation to the main generator, right? Now you can see this, that this is here, that how the generator is being feeding power to the grid, and what happens when there is a loss of excitation. So you can see here that this is your mechanical power input to the generator, and we are also feeding the exciter the IF field current, right? And because of this, the real power is being produced and is fed to the grid, and this real power in fact is produced because of the mechanical power input. So they are closely interlinked. And similarly your QE, the reactive power, is produced because of the field excitation in the rotor circuit or a field circuit. Okay. Now when the field current is being fed, now the generator is supplying both real and reactive power, which we can see the phasor diagram, the real power and the reactive power, and both are produced and fed to the grid. As soon as the excitation is lost, then what happens? This field current IF becomes equal to 0. So when this IF becomes equal to 0, now the generator starts drawing the reactive power from the grid. Okay, now QE will be drawn from the grid. So how the generator will operate? Now the generator will operate, you can see here, as soon as the field current becomes 0, So your QLOE, that is the reactive power because of the loss of excitation, will be drawn by the generator, and in fact when the generator will draw the reactive power from the grid, it will act as an induction generator, right? It will act as an induction generator. So therefore, under this condition, your speed, the speed of the generator, little bit, it will be increased more than a little bit increased than the synchronous speed ns, right? Okay, so now your reactive power is lagging to the generator. So you can see here now the reactive power is being drawn from the grid. Okay, so now the simplest method by which the loss of excitation can be detected, in fact this is not very, though it is not very serious, but in fact the generator, the synchronous generator is designed in such a way that it should act like a synchronous generator. So not like an induction generator, that in fact causes the problem. So therefore we need to detect this loss of it. So the simplest method by which the loss of excitation can be detected is to monitor the field current of the generator. Okay. So if the field current falls below a threshold, a loss of field signal can be raised. A complicating factor in this protection is the slip frequency current induced in the event of loss of excitation and running the generator as an induction generator. So the quantity which changes most when a generator loses field excitation is the impedance measured at the stator terminal. So this is the quantity which we can measure and detect the loss of excitation. So when the impedance is measured at the terminal of a generator, under normal condition the impedance in fact lies in the first quadrant, right? So in the loss of excitation, the terminal voltage begins to decrease and the current begins to increase. So that results in decrease of impedance and also change of power factor. So what happens, the impedance decreases, and because of the decrease in the terminal voltage and increase in the current, and the power factor also changes from leading to lagging, right? Thus loss of excitation can be unambiguously detected by a Moore relay located at the generator terminal. So with a different setting of the Moore relay, it is very easily we can identify. But you can see here how a loss of excitation can be detected. It is the generator which is connected to the grid, right? And now here the Moore relay is connected. We call this offset Moore relay because it functions in a different way, right? So the Moore relay is being fed from a CT and from a PT. So then Moore relay gives signal to the circuit breaker of the generator. So this Moore relay, in fact, it lies in the fourth quadrant and the third quadrant, right? You will see the locus of the Moore relay. So now the locus, it is in fact the periphery of the Moore relay. The circumference of the Moore relay is not touching the origin, and in fact it is separated by xd dash by 2. Therefore it is called offset Moore relay. And we can see here the characteristic of the impedance, how it is varying under different initial operating condition. So this is in fact for the rated initial output, right? And the impedance characteristic is for medium initial output, and this impedance characteristic is for the low initial output, right? So the locus of apparent impedance is plotted, and when the loss of excitation happens, in fact all the characteristic of the impedance that merges towards the tripping zone of the Moore relay, offset Moore relay, and therefore it detects and it gives the trip signal to the circuit breaker. So now we can see the loss of prime mover. When the loss of prime mover happens, what happens in fact? So already we have seen that whatever mechanical input we give, that is in fact converted to the real power output of the generator and the losses in the generator, and the excitation is in fact converted in terms of the reactive power, and the mechanical power input is converted to the real power. Now if we think somehow if the mechanical input, the loss of prime mover happens, so what will happen? So now if we'll say that the prime mover fails somehow, or the steam supply to the turbine fails, then what happens? Now the motor will draw the mechanical power, the motor will draw the real power, the generator, the synchronous generator will draw the real power from the grid now, right? Whereas it is producing the reactive power, but it will draw the real power from the grid, and therefore it will act as a motor. So it will be a synchronous generator, and when it will act as a motor, it will act as a synchronous generator, right? So therefore you can say the power flow condition changes, right? So real power is flowing now from grid to the machine, right? So now what happens? How we can detect this kind of, because the power is flowing in the reverse direction, now the current will flow also in the reverse direction. So if we'll put here one directional relay which can detect the change in the current, then we can detect very well the loss of prime mover, right? So here it is, the loss of prime mover happens when, and we have connected here a directional relay to detect the loss of prime mover, right? So this is the prime mover which is connected to the generator, and the generator is supplying power to the grid. Now in this case your MTA should be 180 degree, right? In that case, if we'll make the MTA, already we have discussed, the MTA is your maximum torque angle. So this MTA, if we'll make 180 degree, then your trip region will be to detect the reverse flow of current, right? Not the original flow of current. So it will detect then the reverse flow of current, and when the current flows in the reverse direction, then it trips the circuit breaker, right? So therefore this is the directional relay with MTA 180 degree, and it gives the trip signal to the circuit breaker. It trips the generator whenever there is a reverse flow of current, that we can see here. The current IA, when it reverses the direction, right? In fact, we are considering under normal condition, the generator is generating under unity power factor, and when the current flow reverses, right? So then it detects and it lies in the trip region, and therefore it gives the signal to the circuit breaker to trip the generator. So this is how it detects the loss of prime mover, and then it trips the generator. Another phenomena is overspeeding. That is also an abnormal operating condition, overspeeding. So how this overspeeding phenomena can be detected? In fact, overspeeding, how it happens? This overspeeding happens when there is a loss of load, right? Loss of load on generator. So this loss of load, in fact we cannot say, because the power grid is very uncertain. So loss of load may happen at any time. So when the load decreases drastically, as the input power is constant, input mechanical power is constant, therefore the speed, the rotor becomes overspeed, it accelerates, right? So it can be detected by putting one tacho generator on the shaft, or by the over frequency relay, because the frequency increases when the speed increases, and this can be detected by these two methods. And if it is detected, if the overspeed is detected, then the action taken is the steam supply to the turbine is stopped, and that is by the governor mechanism, and the generator starts or down. Okay, so most of the time it is not the case of shutting down of the generator. The governor takes action to stop the steam supply to the turbine. So this is how the overspeeding phenomena is being detected in a generator, and the generator can be protected through this mechanism. Okay, so up to this we talked about the generator protection. First we talked about the differential protection and how the differential protection schemes can be used in case of transformers. Then we talked about the busbar protection, how the differential schemes can be used in the busbar protection. Then we talked about the protection of another equipment that is called the generator, which is very essential, which is very important for our power system. And this is how we completed the generator protection schemes. And now overall we completed most of the things, right? Like all the like your overcurrent relay, how a distribution network can be protected, how the transmission network can be protected, how the different elements of the power system can be protected, like transformer, busbar and generator. Now we'll talk more about the relay, evolution of relays. Previously I have shown you that we talked more about the electromechanical relays. Now as the inventions took place regarding the static components, like in case of electronics, we developed the transistors, the op-amps. Then the static comparators came into picture, and the static comparators in fact plays very important role as relay. So then next we'll see how these static comparators in fact plays very important role, how we can implement these static comparators as relays. So first of all we'll see what are the static comparators and how it can be implemented as different types of relays, like whatever relay we have studied till now, like your overcurrent relay, right? We have studied overcurrent relay, then your distance relay, right? Then differential relay. Differential relay is nothing but it is the extension of the overcurrent relay, because we use the overcurrent relay in the differential relay. So we'll see how these different kinds of relays can be implemented using the static comparators. Okay. So let us see the one analysis of comparison versus computation. So an overcurrent relay in fact compares the magnitude of current, right? We compare the magnitude of the current with a threshold value with a reference value. With this we call it a set value and it operates if the current is more than the set value. That is in fact a comparison. And a directional relay compares the phase angle of the measured quantity, that is current, with a reference phasor, that is voltage, and operates if this phase angle exceeds a predetermined threshold, right? So a simple impedance relay compares the torque generated by the current, operating torque, with the torque generated by the voltage that produces the restraining torque at the relay location, and operates if the operating torque is greater than the restraining torque. Already we discussed all these things. So all the relays perform some or other kind of comparison, if we'll see, right? So thus at the heart of any relay there is always a comparator. We are always comparing the measured quantity with the threshold quantity, right? So historically these comparators were implemented using electromechanical technology. Already we have seen this kind of technology, we discussed all these things. But eventually the electromechanical relays gave way to the solid state relays, and an alternative strategy to comparison is to perform direct numerical computation. If we are not doing comparison, So that is if we make the direct numerical computation. However, in the past, when the electromechanical relays were being widely used, it was not possible to perform the numerical computation in a relay. So the comparators helped in avoiding the direct numerical computation. So the relays based on the comparators were found to be quite simple and robust. So we will see both. We will see also the numerical relay, which in fact computes, and we will see the static relays, which in fact used as comparators. This gave rise to the technology of protective relays built around the comparators. Considering the comparator as the basic building block, how different relays can be designed. So the comparator based relays are very attractive because of their inherent simplicity and low cost. However, they suffer from drawbacks, since a comparator based relay essentially give a go no go type decision. The fault cannot be precisely located. So this is just, it will give the signal, right? It is very difficult to change a comparator based static relay to another type relay. It has no flexibility of such kind of conversion. So the comparators can be classified into two types, those based on comparison of amplitudes and another kind based on the comparison of the phase angle. So let us talk about the amplitude comparator. So if we have two signals and we know the amplitude, then the trip loss is if your SO, that is the operating signal, is greater than the restraining signal, then it trips, else restrain. So if we will have a building block of amplitude comparator, then if you have two signal having amplitude SO and SR, okay. So SO means it is the operating signal and SR is your restraining signal. Then it gives the trip signal if your SO, the magnitude of SO becomes greater than the magnitude of SR. So like we can see here, this will be your tripping region and this will be your restraining region. When we have a threshold value of SR and SO is lying within the restraining zone, then your comparator will give the restraining signal, it will restrain and when it is outside the restraining zone, it gives a trip signal. Similarly, we can see the comparisons. It doesn't matter where the phase angle is, right? Like if we'll see the phase angle, it is different for each case, but in each case the magnitude of operating signal is greater than the magnitude of the restraining signal. Therefore, it will give the trip signal. So these are the cases of tripping cases, right? When your SO, the magnitude of SO is greater than the magnitude of SR. Similarly here, these are the cases of restraining conditions, right? When the magnitude of SO is less than the magnitude of SR. Wherever it lies, it doesn't matter, right? Okay. So therefore, these are the condition of restraint. Now these are the condition of threshold when the magnitude of SO is equal to the magnitude of SR, right? These are threshold conditions. So now we'll see the phase comparator, how it works. In fact, your phase comparators are of two types. One we call cosine type and other is your sine type comparator. So in case of cosine type of comparator, if your angle between the measured quantity and the polar quantity, it lies between minus 90 degree and plus 90 degree, then we call it cosine type of phase comparator, and then it gives the trip signal. So argument ARG indicates the argument of SM by SP. That means the phase angle difference between the measured signal and the polar signal. If it lies between minus 90 degree and plus 90 degree, then it gives the trip signal, else it restrains. So if we'll have a block diagram of cosine type phase comparator and we are giving two signal, one is measured signal and other is polar signal, then it gives the trip signal when the argument of SM by SP is lying minus 90 degree to plus 90 degree. That means that this will be your trip region, right? So this is your restraining region. Whenever your SM is lying in this region, that then your comparator is restraining, and when it is lying in this region, in this zone, then it is a trip, it is giving trip signal, right? So then we can say that these are all trip cases where the argument of SM by SP is lying within minus 90 to plus 90. That means it is less than minus 90 degree and greater than less than plus 90 degree and greater than minus 90 degree, right? Now if we'll see another case, these are the cases of restraint where your argument of SM by SP is in fact lying outside the region of minus 90 to plus 90. Here in this case it is equal to 180 degree, this is also 180 degree. The magnitude here is not a matter, it doesn't matter whether the magnitude is greater or small, right? So here the argument is greater than 90 degree, here it is in fact should be less than minus 90 degree, right? Okay, therefore it is restraining. So now if we'll see, these are the threshold conditions where the argument of SM by SP is equal to 90 degree and here it is equal to minus 90 degree. They are threshold conditions. Okay. So now if we'll see the sine type phase comparator, in case of sine type phase comparator, the trip law is it should lie within 0 to 180 degree. That means the argument of SM by SP should lie between 0 degree to 180 degree, then it trips. So this is your sine comparator, this is your measured signal, polar signal, and this is a case of restraining because the SM is in fact greater than this is the trip zone, this is the restraining zone, and SM is lying from 0 to 180 degree, therefore it is trip condition. It is a trip condition, right? So similarly here in this case, this is also a trip condition, this is also a trip condition because they are lying from 0 to 180 degree. And similarly if we will see, these are all restraining condition because SM and the phase angle between SM and SP is greater than 180 degree, right? And similarly here this is a threshold condition because SM is lying with SP, that is the angle between this is 0 degree. This is also a restraining condition because phase angle between SP and SM is greater than 180 degree. This is a threshold condition with different magnitudes we can see here, and magnitude here doesn't matter because this is a phase comparator, right? So okay, we'll stop here and we'll continue with the static comparators as relay. In the next class we'll see how we can implement the static comparators as relays. So in the next class, lecture number 26. So thank you very much. Thanks a lot for your kind attention.